So, good afternoon for everybody again. So, it was, I guess, in 2018 at our conference in Tatranská Lomnica when we had conference about astrophysics with small telescopes, and also Ernst Pollmann was here and suggested me that I should come here to attend your conference in Vega in the next year or so. But therefore, in fact, I am here. I'm lucky that I can also inform you about some my recent results that are based on observations, mainly spectroscopic observations with small telescopes made by mostly amateur astronomers. So in my presentation, this is the goal of my presentation, to demonstrate how these observations with small telescopes can be used for, I think, good, worthy science. And I selected the cases of exploding stars, classical novae, and some symbiotic stars, because these events are attractive for everybody, yes, not only for amateurs, for everybody, because they are rapid changes, spectrum changes, and it is always very interesting. So I selected the outbursts that are running on the surface of the white dwarfs. So as everybody knows, just a few sentences about what the white dwarf and how get the white dwarf from normal stars. So if you know, this is some artistic sketch of evolution of the Sun-like star from the interstellar material. Oh, sorry, from the interstellar material through the present stage on the my sequence, and through the giant star here, and finally when the fuel for thermonuclear fusion is already exhausted for these relatively small massive stars, so hydrogen in the core, hydrogen in the envelope, and also helium in the core cannot already are fused to higher elements or carbon. Then there is no balance between the pressure of radiation and the weight of outer layers. Therefore, the core of the star starts collapsing. Then the gravitational potential energy is released, which makes the central core hotter and hotter at the beginning of the stage, and also more luminous, which results for the expelling of the outer material, and we observe the object we know as planetary nebulae. And at the beginning, the star, the end, which doesn't have any more fuel for thermonuclear fusion, so it is getting cooler and cooler, and finally ends as a black dwarf. But what is interesting and important is that such the object has an extreme gravity on its surface, because very relatively high mass, comparable to the mass of the our Sun, depending on the original mass, of course, but the radius is only, to say, 1/100th of solar radius. Therefore, the gravity is extreme. Okay, but if such the object, the white dwarf, with such extreme gravity is a member of a binary, so if it can get additional material as a fuel, this dramatically changes the situation. So therefore, in these cases, I feel, yes, I selected two cases as example of outbursts on the surface of white dwarfs. One is the case of very close cataclysmic variable, which the orbital period of which is around the hours. The donor is my sequence star, the white dwarf is a crater, and the mass transfer mode goes through the Roche lobe overflow with the rates around 10⁻⁸, or much smaller, 10 to -10 solar masses per year. And occasionally we can observe, as a result of such long-term accretion on the surface of the white dwarf, the so-called classical nova explosions. And another case, the case of systems when the white dwarf is in the system of its orbital period in order of years, and the donor of material that is accreting on the white dwarf is the red giant. White dwarf is the common, but due to the very large distance, the separation of white dwarf and red giant, the accretion comes from the wind from the giant at usually much larger rates. And we can observe the so-called Z Andromeda type of outburst. Yes, the bottom shows just the sketch. So the separation in such a cataclysmic variable is a few solar radii, while when for the symbiotic stars we have separation of few astronomical units or more. The red giant losing the wind at the relatively high rates, which we know from the radio observations, also for other modeling, that the rates can be as high as 10⁻⁷ solar masses per year, and the white dwarf that is accreting a fraction of this material, which makes very luminous and very hot the white dwarfs. As a result, the white dwarf ionizes the circumstellar environment, and but it is not for us very important. So what in fact is happening? What can happen? What we can expect when the material is accreting on the white dwarf? It depends on two basic parameters. On that, how much was the rate of accretion, and what is the mass of the accreting object, mass of the white dwarf. This was a question for many people, many astronomers engaged in this problem during last century. There was many papers by Paczynski, Žitkov, other astronomers, Japanese, led by Fujimoto groups and so on. And basically, they found this. They found this interesting graph, the dependence of the accretion rate on the mass of the white dwarf. And basically, this region can be divided into two parts by this solid thick line, and this green arrow shows the part when the material is accreting on the white dwarf at relatively low rates. 10⁻⁸, 10⁻⁹, 10⁻⁻10. It is accreting, and the mass of the accreted envelope is gradually increasing up to a point when the mass of the accreted material is so large, then at the bottom of this accreted material there is a critical pressure for ignition of nuclear fusion, and we can eventually observe the event of the nova outburst. And it was found that if the accretion is higher than this solid thick line and lower than this solid thin line, then the burning rate, nuclear burning rate, is equivalent to the accreting rate. So the material is burned as it is accreting. This regime is called as stable burning of material, which corresponds to the certain. This is a relatively narrow band, yes, but we observe and we think that many symbiotic stars produce the energy from this type of accretion. So here this is I forgot to emphasize the energy output. So in this case it is easy to find taking a typical accretion rate for mass. We can get the total luminosity which comes only from accretion, so which is in order of a few solar units or maybe a few tens solar luminosities. But in the case when the hydrogen-rich material which is accreting on the white dwarf surface is burning, then we can get much more, nearly 2 orders of magnitude higher energetic production than in the case of net accretion. Yes, the important parameter is that we know that from 1 gram of net hydrogen we get 6.3 10 to 18 ergs per gram. Yes, but if the material is not only from hydrogen, then simply we multiply this constant, multiply to amount of accreting material. For example, this is order of 10 to 18. So if we have accretion rate here is to say 10 to minus 7 solar masses per year, which is some a few to 10 to 18 and nearly 10 to 19. So 10 to 19 and 18, this is 10 to 36, 37, which is in order of thousands solar units, which is a typical luminosity of such stably burning white dwarfs. Okay, and it can happen sometimes that the accretion rate can be even larger, because in the case maybe of symbiotic stars, where the donor star is the giant, which is unstable object, sometimes can happen that more material is accreted, I mean above the upper limit for stable burning, and in this case it was shown that the white dwarf pseudophotosphere is blowing up to the giant's radii, or it is expelling a lot of material in the form of the wind. It is the case, as I will show later, the case of the so-called ant-type outbursts. But to state this, we need, of course, to derive parameters. we need to estimate well the luminosity during the outburst, which is really problem. And okay, so the dotted line is the Eddington limit, which is the limit when the luminosity is larger than the gravity, and there is a strong outflow. It usually is the case of nova outbursts. And finally, I have fourth stage. It is the point which is still under debate. What will happen when the accreting white dwarf will reach or if the accreting white dwarf reach the critical Chandrasekhar limit, and if this happens, then the collapse starting the ignition of all the fuel from carbon, oxygen, and we observe the supernova 1A explosion. But we all, or majority part, astronomers who are engaged in these problems believe that it is so, but still also I think that it is the case that the symbiotic stars, when the accreting material, also nova, yes, nova object, when accreting at very low accretion rates, can gradually reach the Chandrasekhar limit and explode. But the problem is what will be happen during the explosion, because one important parameter is the amount of mass which is expelled. And the question is if also the fraction of the ash of this fusion is also expelled away. Because you can imagine that when the nova starts, then after the one nova outburst, then additional after, to say, depending on the accretion rate and mass, thousands or hundreds of thousands years, nova can again erupt, and it is a question, yes, if the material will be increasing. Also, there can be helium flashes, because helium, this is the ash of the hydrogen burning, the hydrogen fusion. So, but there are some papers that are stating that in spite of hydrogen flashes, helium flashes, that the accreting white dwarf in this system can really reach the Chandrasekhar limit. Okay, this was just. Okay. So I selected two objects. One is the classical nova, V339 Delfini, and on this case I will demonstrate how to analyze the spectroscopic observations and evolution of such nova. Here is just for illustration the light curves from our SO database in two colors, in B and IC. And the bottom panel shows that light curves UBV for the well-known classical symbiotic star H.E. Pegasus, which is also known as the slowest symbiotic nova, which started as a nova with the nova outburst in sometimes 1850, I think. And during the end of the last century, some 90 decade, it already was in the quiescent phase, showing these variations. Yesterday, Jaroslav showed and demonstrated these typical orbitally related variations during this so-called quiescent phase. But after 165 years after the nova explosion, the AG Pegasi showed new, the half of 2015, new outburst, but it was not a classical nova outburst, it was the Z and type outburst. Only a few magnitudes, which is the difference between the classical nova outbursts. We usually observe the difference magnitude around from 7 to 15 or so. Very high energy production, but this number is extreme. It is connected just to this nova, and very high mass outflow at the beginning at the rate of 10 to minus 4 solar masses per year, while for the classical symbiotic stars, Z and type outburst, we measure brightenings by a few magnitudes depending on the color, and luminosities that are below, usually below the Eddington luminosity, but relatively also large. And mass outflow about 2 orders magnitude below those measured usually for classical nova. So the major diversity is the violence of these outbursts between nova-like outbursts or classical nova outbursts and the Z and type outburst. Yeah, this is just for illustration. I summarized for your imagination another 2 classical symbiotic stars, Z and H Draconis, which shows these Z and type outbursts time to time. Then it is interrupted by the quiescent phase. We observed some wavy-like variations, and again outburst of Z and type. Z and is a prototype of symbiotic stars, and from a historical point of view, it was observed a long time ago, and showed in visual band such brightenings. So these brightenings were called as Z and type. Yeah, this is just from the past investigation. It is interesting. There are a lot of open questions. Yes, interesting. For example, that this is a multiple brightenings, and the question is why, how these brightenings can be kept, and so on and so on. But this is just for imagination. How does this light curves of classical symbiotic stars looks like? And what is the common is the mass loss. In the case of classical nova outburst, this is this case of nova Delfini 2013, called V339 Delfini. The mass loss, the terminal velocities from the H alpha line was around 3,000 kilometers, while for H Pegasi during the Z and type outburst, the terminal velocity was something more than 1,000 kilometers per second. Mass outflow is indicated in many cases directly by the Signet type profile, with mainly at the beginning of the outburst by this absorption component. The case of H Pegasi, this is the binary which has relatively low orbital inclination, so it is seen more or less pole on. And for a comparison, the blue profile is measured during the quiescent phase, and the red one is from the 2015 outburst of the stars, and we clearly see that there is a significant mass outflow, which is possible to quantify and determine the mass loss rate during outburst. Yes, there are some also the spectra with made by small telescope. I summarize here somewhere, and later I will show the paper with all co-authors who contributed to this research. This was the line, and basically what is happening in the continuum, because the nova, such outbursts, the light during the outburst is composed of more components of radiation. Yes, and these components are evolving during the time. This is very important. Yes, here just for demonstration I draw what possible is from the harder X-rays, from non-thermal plasma, extremely hot plasma, then radiation from the burning white dwarf with this temperature, then some converted radiation in the form of nebular radiation, and in the case of the symbiotic stars, we have the spectrum from the giant, and possibly also dust component, always seen in the so-called D-type symbiotic stars, but it can be created and emerge during the classical nova outburst. But what is important is that these all components changes during the outburst, and I will now demonstrate what we observed, how they are changes. Because, for example, here I just for the sake of to demonstrate how narrow is the part of the optical observations. Yes, and of course this is the log scale. Generally during the maximum at the beginning or at the very beginning of each outburst, this light from the auto-exploding star is usually concentrated in the optical. It is very interesting because it can be directly and easily measured. And if we have major part of energy produced in the optical, we can very easily and relatively precisely determine the luminosity, which is much more difficult when we observe the extremely hot burning white dwarf, because we know simultaneous observations from X-ray and so on, which is always difficult from the point of view of observations. So, just illustrative example. This is the symbiotic nova RR telescopy. This is just example of the sketch before that really this exists. This is observations made by XMM Newton from X-rays. This is approximation by a model or simple also black body, which corresponds to the temperature of around 100,060 kelvins. Then observations by satellites and also in optical shows the strong contribution for nebular radiation, which represents the converted radiation or fraction of the converted radiation of the hot ionizing source, and the giant star and the dust component. This is just for illustration that really we observed something like this. Yeah. Go back to the case of Nova Delfini 2013 with free Delfini. Here the light curve, but in log scale, and it is very convenient to use dates along the evolution. Yes, usually the day 0 is connected with the discovery day, or in some cases the day 0 can be the maximum. Yes. And then the phase when the nova radiates mainly in the optical region is called the fireball phase. Then the spectrum is gradually changing because the explosion, during the explosion, a lot of material is expelled, and at the beginning is usually optically thick, and we observe the relatively cool and very large pseudophotosphere. Therefore, this phase is called fireball phase, and during that time, as the material, the explode material is extending, the optical depth is lowering, and we can see deeper and deeper, and the radius is smaller and smaller. Hotter and hotter is the pseudophotosphere, and we measure the spectrum from the transition. Then it is known the super soft source phase, when the extreme hot white dwarf radiates at super soft X-ray wavelengths, to say from 10 angstrom to 30, 60 angstrom. Yes, this is a question of detection, because there is usually very large absorption, so it is often difficult to measure this part. And in this case of this nova, it was very interesting that simultaneously with this super soft X-ray source phase, we measured also the dust emission. So simultaneously with this phase. Okay. So how the spectrum would, now I will show you how the spectrum looks like during the fireball phase and following phases. So this is fireball stage. At the beginning of the fireball stage, day 1.9. Yes? So the maximum production of the energy is in the optical. Yes, and it is really possible to compare the observation, which is the spectrum magenta or photometry, to the model. It is simple Kurut's model, atmospheric model. Yeah? And the spectrum, it was in relative units. And it is quite enough. Yes, it needed to be absolutely calibrated. Yes, but important is that it is at least in relative units, and having simultaneous photometric observations, which can be converted to fluxes. So in this case, then it is enough 1 point, for example, V, and we scale the spectrum to this point, and you get the absolute units here. But of course, better is to check with multicolor photometric observations. This is the spectrum. The brightness was the maximum at 5 magnitudes, I think. Spectrum of a small telescope, 0.355 meter. Yes. So, what we can get, yes, you know probably that the profile of such a spectrum depends on the effective temperature. So, how does it look like? Says us what's the effective temperature of this pseudophotosphere. Then we have amount of this energy. So by this way, we scale the model to observations and get informations about the radius, and having the radius and temperature, we can derive the luminosity. So basic fundamental parameters. What I said is I said just this, what is schematic here. Here is the spectrum, and this is the synthetic spectrum, yes, Kurut's model, for example, and this is the scaling factor, how much of this energy. So, from the synthetic spectrum, which fits the profiles, we have effective temperature. From the scaling, which is the angular radius of the white dwarf pseudophotosphere, we have effective radius of the white dwarf. Of course, we need to know what's the distance, which is often problem was the distance, reddening, yes, the first important points which we need to know. So by this comparison, we get two fundamental parameters of the pseudophotosphere, which radiates at the very beginning, usually within the optical region, which is very convenient. And this is the same, but later, during the fireball case, day 5, and these observations, 0.4 meter telescope, this observation scaled to this photometry, simultaneous photometry, corresponds to the lower temperature, yes. Here it was, yes, here it was 12,000 kelvins, and the effective radius of the pseudophotosphere was something more than 100 solar radii, but later on, some 4 days later, we got that the effective temperature around 7,000 Kelvin and much more expanded pseudophotosphere. Yes, with this basic evolution during the so-called fireball case. Okay, this is the summary. Here we have the fireball stage, more spectra from the very beginning. Yes, the scaling is always the same to compare directly how much it is radiating. And this fireball stage lasted about 6 days, August 14 to August 20. So we just compared the observations with the synthetic spectrum. Observations, blue line is atmospheric model, green line is nebular radiation, which starts to be seen during the transition to the harder spectrum, which followed this, the last spectrum, day 6 after the discovery. There was temperature around 6,000 kelvins only, and later this pseudophotosphere was diluting, and we could observe much higher. The energy was shifting to shorter wavelengths, and the bottom row shows the spectral energy distribution within the optical, where we already detected relatively large amount of nebular radiation, because the central source, central burning white dwarf, was much hotter and still very luminous, so ionizing the outer parts, and therefore we observed relatively very high so-called emission measure. So the amount of converted radiation of the white dwarf is also corresponded to extremely high luminosity. But we need to model these two components of radiation, one component of the shell of the white dwarf, which is however difficult only in the optical, and with the nebular radiation. So this is just a summary of all the parameters, how the fundamental parameters were evolving along the along the evolution of the brightness in the V. This is the temperature in kilokelvins, 10,000 kelvins over 6,000, and the luminosity from 10 to 38. 38 maximum was very high, much higher than the Eddington luminosity, and the effective radius was gradually increasing in this case. These results were published already in 2014, and all observers contributing to this work were co-author of this paper. Practically, yes, this paper was practically based only on the data collected by amateur astronomers. And later, what is happening, what we observe later after the fireball phase and after the transition, also so-called iron to curtain phase later on. Here, this was the day 35. We started to observe the X-rays, but also in the near infrared. Yes, at day 35, there was a small contribution from the dust. To get the energy distribution to model, we needed some dust radiation at the temperature of around 1000 Kelvin. And what was interesting, that from day 72, the two components of dust were measured. And the most interesting point here is that the strong dust emission developed in the near-infrared spectrum during the transition from the harder spectrum to the super soft X-ray source phase, when this existed along the simultaneously with the very strong source of ionizing radiation. So it is very interesting part. Here is the model within the UV and near infrared part, which clearly show the presence of the two components from the dust. Optical part to Balmer jump, and the UV by HST spectrum. Nebula was very hot, which is given by the steep profile. This is green line. Yes. Emission measure was still very high, and cooler dust and hotter dust closer here. And altogether, with the XMM observations, practically simultaneous observations during day 100, yes, we get such picture, and the luminosity of the burning white dwarf is confirmed. And what is very interesting, that even for this day, which is relatively very long time after the discovery of the outburst, was still extremely high luminosity, 10 times than the Eddington luminosity. It is simply something unusual, because this is against the theoretical predictions that if the Eddington luminosity is reached, then it can be reached only for a very short time of hours or days, and then is gradually going down. So the question is, what is keeping such the high luminosity for such a long time? This is one open problem which is not still solved today. Yes. Okay. Yes. The temperature is very high here. Of course, the effective radius still is relatively high. Yes. 2/10 of solar radii. And interesting and important point is that the amount of absorbing hydrogen is nearly equal to that of the interstellar amount, which supports the correctness of this model. And later, yes, the basic question is how to explain the simultaneous presence of the dust and extremely high luminosity and hot source of the burning white dwarf. Because it is known, and there are some publications, that the dust in the field of such radiation cannot survive for a long time. A few days, or depending, of course, of parameters. I remember that the maximum was perhaps 50, 60 days in maximum for typical. But here we have 100 days, and dust existed even much more, but we didn't observation like here. So the only possibility is, only I do not know, I think, I suggest that the dust particles must be somewhere covered, somewhere shielded from the hot radiation of the extreme luminous burning white dwarf. And one possibility is that there is a disk that is created from the beginning of the explosion. And from the measuring, we measured that the velocity from the fireball stage, the figure I showed, these P Cygni profiles, absorption corresponded to the velocities of 1,000 kilometers, then was gradually decreasing to 600 kilometers per second, and in this way were ejected. It was the slow outflow, but the hydrogen lines, the other line suggested that the wind driven by the radiation of the white dwarf has the much higher velocity, around 3,000 kilometers per second. And there's a theory that when such the high velocity wind particles interact with the low velocity particles, that both shocks creates, here this is the orange line, here, this figure, and in this case there can be conditions arise so that the density can be 3 orders of magnitude higher. Also temperature goes by the same factor lower, which makes good conditions for creation of the dust. Usually the limiting temperatures for the dust, depending of the nature of the dust, the composition and so on, it is around 160 Kelvin and so on, yes, but we have the radiation field of 100,000 Kelvins, yes. So it is the possible case that we need 2 different types of outflow. One small outflow and another one with high outflow, and interaction with this different outflow can create conditions for creating the dust which is in the disk, equatorial disk, and it is somehow shielded from the hot luminous white dwarfs. And it also would explain the case that the part of the dusty disk is which is closer to the white dwarf, it will be probably hotter, and gradually it will be melting, and the farther part is cooler, and that is why we probably therefore we measure the hotter dust, which is in the disk closer to the white dwarf, and the cooler dust, which is the at more distances of the white dwarf. Okay. So this is one of the possible explanations, I think. Another evolution, finally, it is the so-called nebular phase, practically to the end, but we do not know what is the end of the nova. Yes, it is still, and it is really takes long time when the brightness is comparable with the brightness of the progenitor. The progenitor was about 17 magnitude. Yes, somewhere here. Yes, but we still observe something. And the ejecta, the original ejecta, is very small densities, so they are good conditions for creation of also forbidden lines by collisions, and therefore we call this stage by nebular stage. Strong emission lines. There are 3 cases. This nova was intensively observed and studied. So we got observations from HST at day 248, nearly 1 year, 1.5 years after the discovery, and nearly 2 years after the discovery. Still, and what we observed just gradual decrease of the temperature of the white dwarf, its luminosity, and also the radius. The source of data, optical photometry from ASO and optical spectra, was supplied here by one Japanese amateur using 40 centimeter telescope, Fuji Kurosakoi Observatory. I'm not sure is the name. It was Masaki Fuji. Okay. Now, example. This was the example of classical nova explosion. The case of V339 Delfini, and now go back to. May I have time? Yeah. Okay, no problem. Okay. So finally, I would like to demonstrate the cases of outbursts, of Z-ant type outbursts we observe for this star, which was practically not known as a symbiotic star. It was a neglected star, and originally, I mean, to this event, to the August 2018, it was in catalogs classified as H alpha emission star, nothing more. And by automatic all-sky automated survey for supernova, ASAS-N indicated rapid brightening by a few magnitudes different. I think in V, but then we immediately started observations at the Scarlet Pleso Observatory and received this UBVRI light curves, which confirmed the nature of this outburst as Z-ant type outburst, which is characterized by relatively small brightenings only of a few magnitudes and gradual fading. The same happened. There was some surprise that A.G. Pegasi, that was known as the very slow symbiotic nova, which started its activity already in, I said, 1850 as nova-like burst, outburst, then was gradually fading, and here already in quiescent phase. But suddenly in June 2015, it showed for the first time, sorry, not again, but for the first time, the Z-ant type outburst. After the nova-like outburst 165 years ago, it showed for the first time Z-ant type outburst. It was also very interesting. Why? Why not another nova-like outburst? Why just this Z-ant type outburst? Yes, this was one important question. Something more. This is light curves of A.G. Pegasi in details, covering just the activity, just the outburst, which was 2 peaks. One peak was in half of 2015, and second peak started in October that year, and then gradually was fading and changed to variations of classical quiescent phase. And here the case of this HPH alpha 170405 star, now known as V746 Sagittae, showed the peak, but only one peak. This is only the starting, the beginning of the quiescent phase, and another observation shows such wavy-like variation, which is not shown here because it is somewhat older picture. And okay, and the right panel shows the energy distribution during the outbursts for H.G. Pegasi and for V426 Sagittae here, and for the comparison during the quiescent phase. Yes, and we can see that at the very beginning of the outburst, somewhere here for H.G. Pegasi, and the same for this star, immediately very strong contribution from the nebula was seen. No optically thick pseudophotosphere as in the case of the nova or in the case of other symbiotics. Yes, this is just a special case. This is another story and another lecture, why and so on. And we can see that there are basic parameters which can be derived from the energy distribution, modeling amount of emission, which depends on the volume and concentrations of electrons and protons or ions. Yes, this is the so-called emission measure, amount of this converted radiation from the burning white dwarf. And from indirect method, using the line emissions H beta and helium-2, both stars showed relatively strong helium-2 lines. I do not know which just it is, there are more lines, yes, but you know helium-2 4686 and H beta. And in this case, when all the photons, yes, if the lines are optically seen, so if we observe all the converted photons by this line transition, yes, which is not quite true because they are optically thick lines, we can estimate the temperature, which was around, at the beginning, 200,000 kelvins. Yes? And from indirect method, assuming that all ionizing photons are converted to the emission measure, then we can estimate the luminosity. Knowing the temperature, knowing the emission measure, then the luminosity, which is nearly or very close to the Eddington luminosity, which is very interesting and very important parameter for interpretation of the Z-ant type outburst. It was not known for a long time because mostly emission lines were used to estimate the luminosities, which in many cases underestimated values because the emission lines are much more opaque than the continuum. Therefore, usual or typical luminosities were in nearly one order of magnitude lower. So this was question, how to interpret the Z-ant type outbursts. If we have luminosity relatively slow as a few 10 to 36, yes. But if we're using a new approach, using the emission in the continuum, which is optically thinner than that from the lines, we get much higher luminosity, which is possible to interpret as the additional accretion to that which is causing the stable burning on the white dwarf surface. Okay. From modeling of lines and the emission measure, we can estimate that during the outburst, about a few 10⁻⁶ solar masses, mass outflow was high in the form of the wind. In the quiescent phase, the parameters are at least 1 order of magnitude lower, but the temperature is still relatively very high. Yes. And small radius, effective radius. Yes. The luminosity is 1 order of magnitude lower, which corresponds to the stable burning, to the accretion rate of a few 10⁻⁸, nearly 10⁻⁷ solar masses per year. And mass loss rate also nearly 2 orders lower than during the outbursts. So the outbursts are characterized by strong mass outflow, brightening, and higher luminosity of the white dwarf. Oh, perhaps again, I already showed this figure, this broadening of the line, which is possible to model by the spherically symmetric wind, which is ionized by the central source, and from, if we know some prediction how the particles are accelerated, so the so-called wind law, yes, then we can model the profile of the wings, which is depending, of course, on more parameters, but basic parameter is the mass loss rate. How much mass is losing per time. Also assuming if the emission measure estimated from the continuum results from such the ionized wind, also we have a relation between emission measure and mass loss rate, and of course again some prediction of the wind law. We can estimate from this parameter also the mass loss rate, which is in order of a few 10⁻⁶ solar masses, pardon, solar masses per year. This spectrum, also very useful spectrum. Important was the timing at the beginning, somewhere at the beginning of the outburst. Yes, spectrum from R phase. Only 20 centimeter telescope. Yeah. And again, some summarization. As I told you that this enhanced accretion above the upper limit of the stable burning causes the strong mass loss rate from the burning white dwarf, which corresponds to luminosity. If we calculate, we take this accretion rate here from the mass of white dwarf mass in symbiotic stars usually are relatively low. Of course, there are some exclusions. Low, it means 1/2 or 6/10 of solar masses. Yeah. So we are somewhere here. So if the m dot exceeds the stable burning limit, optically thick wind or mass outflow, many authors prefer formulation through the optically thick wind as from the white dwarf. Corresponding luminosities are 10⁻�37, which is close to the Eddington luminosity, depending on the mass of the white dwarf. So the luminosity is 10⁻38 Eddington luminosity, multiplying the mass of the object in the solar masses. Yes. Okay, some evolution along the light curves, the parameters, temperature, effective radius, luminosity, and the mass loss. I used a lot of more different approaches, and the average correspond to a few 10 to -6 solar masses per year. This is practically final slide of my presentation. Here I plotted not historical but relatively long-term light curves of the H. Pegasi, V1329 Cygni, and these stars V746 Sagittae. In both these cases, H. Pegasi and these stars, we observe this Z-an type outburst. Yes. In this scale, this is just frightening as 1p. But all these objects experienced in the past the nova-like outburst. The H. Pegasi, it was, as I said, 1850, yes, and gradually it was fading, and after 165 years we measured Z-an type outburst. Yes. In the case 1339 Cygni, the nova-like outburst started in between 1965 or so, but before this stage nothing was observed. It was not known as, it was simply eclipsing star. Yes, no activity. It was not classified here, yes, before this outburst as a symbiotic star. Simply eclipsing binary, nothing more. But later showed this outburst, then evolution to the wavy-like orbitally related variation, which unambiguously classified this object as a classical symbiotic star. And this is the signature that there is a strong accretion rate, which makes the accreting white dwarf very hot and luminous, corresponding to the stable burning on the surface of the white dwarf. The same happened for this case. We analyzed recently these unknown symbiotic stars, and also it was found, this is a new result. Yes, as we started campaign for observing this, my colleague Sergei Shularov, at that time he was just on holiday. It was it was 2018 year eruption. Yes, from the catalogs measured from photographic plates and recognized that there was nova-like outburst. Yes, it is very interesting that the nova-like outburst first, because it is logical, first the white dwarf is accreting at a relatively small ratio, maybe larger rates corresponding to the stable burning, but if there is not such enough material making the critical pressure, yes, then first we have to observe the nova-like or classical nova outburst. Nova-like, it is usually used for symbiotic stars because the amplitude is smaller, because there is a red giant which is contributing to the optical much more than the dwarf as a donor in cataclysmic variable. Yes, so the amplitude in the classical nova are therefore much higher, but if the nova outburst appeared in the symbiotic system, then the brightness change correspond only 7 magnitudes or so, 4-7 magnitude, because the presence of the giant. Okay, so we can speculate here much about what is important. Important is that if the accretion is within the rates for stable burning, then we observe the so-called quiet nuclear burning symbiotic stars. Examples, if the accretion rate exceeds for the transiently only the stable burning accretion rate, that we observe that N-type outburst, which occurs in classical symbiotic stars, and if the accretion rate is below the lower limit for stable burning, that we observe the accretion powered symbiotic stars, usually also called, as yesterday Jaroslav told, accreting only somehow. I prefer accretion powered, but it doesn't matter, NG Andromeda and so on. So this research is very important for also evolution of this type of binaries, to understand different type of outbursts. So the impact of observations with small telescopes is, I think, evident. And that I said here is a short summarization of these 3 papers with significant contributions by amateur astronomers. I used their ARAS database, and without their contributions, I think not such a result could be possible to get, because what is the most important is that first, of course, the bright explosions of accreting white dwarf in symbiotic star or classical or cataclysmic variables are very good targets for the science with small telescope. And strong advantages is the high cadence of observations. The amateurs are very prompt feedback to alerts of some event. Yes. Important supplement to the measurements with satellites, as I demonstrated for this nova, when we had observations from HST and ESO observation and so on. Yes. And also important is the simple direct approach to the data, not as in the case of tests. Okay, so I would finish by this saying that amateur spectroscopy and photometry of bright transients with small telescope can contribute really to world science. Okay, thank you very much.